deixa aqui o...
Chegando, já chegou. Antes de mais nada, eu queria só reforçar para vocês as novas mudanças absurdas no nosso horário, na nossa agenda, mas acho assim que está sendo muito boa, porque nós estamos agregando outras informações que vocês talvez não tivessem, né? Então, só para relembrar, hoje a gente vai ter aula do professor Ettore. Daí, a próxima aula, que seria estudo dirigido, vocês foram muito felizes e sortudos, e nós temos aqui com a gente um engenheiro amigo nosso do Fermilab, que vai, o nosso colaborador, e eu pedi para ele se ele gostaria de conversar com vocês, professor Gustavo, se ele queria conversar com vocês a respeito do trabalho que se faz no Fermilab do ponto de vista de engenharia, né? Aí ele se propôs, então vocês... Na hora do estudo dirigido, ele vai falar com vocês um pouco sobre isso, tá? Então, a gente troca o estudo dirigido, a gente deixa para amanhã. À tarde tem a sessão de pôster, que é o pessoal das outras escolas, mas eu vou estar por aí, se vocês quiserem tirar dúvida, a gente está sempre à disposição. E às 4, a aula do professor Flávio, tá? Isso hoje. Amanhã, se conseguir chegar, porque ele está chegando agora às 9h40 em São Paulo.
Vamos para hoje, às 10h35, para todo mundo subir aqui em frente ao Instituto, que vai ter a foto oficial da escola. Então acabou aqui, já sobe ali para a escada.
Tá bom? Por favor, né? Tô 2 semanas, né? Contato com a gente, pelo menos vocês levam. A gente tem a foto de todo mundo. 10h30, né? Antes do coffee break?
Acabou aqui, já sobe.
Tá. Então você não pode atrasar muito, tá? Mas depois eu boto. Não, tá bom. E aí amanhã, a primeira aula de amanhã, eu tinha pedido para que a gente tivesse um contato com empresas aqui de São Paulo que estão desenvolvendo partes, que estão ajudando na parte de desenvolvimento tecnológico daquilo que a gente faz. O problema é que eles tiveram, como são empresas, né, eles tiveram um imprevisto, não vão poder estar aqui na primeira aula. Mas, como disse, vocês são umas pessoas de muita sorte. Eu conversei com o professor Arnaldo e convenci ele de fazer para vocês aquela conscientização, né? Não vamos dizer aula, né? Uma conscientização sobre o uso de radiação, tá? O uso correto, aquilo que a gente conversou na aula passada, na aula de ontem, tá bom? Então, estejam aqui às 9 e aí vocês vão ter... Eu não vou estar aqui amanhã de manhã, mas à tarde eu tô, tá bem? E aí o estudo dirigido da tarde fica livre para a gente conversar um pouco também. Que também convenci o professor Pedro de estar aqui naquele momento, para que se vocês tivessem dúvida com respeito à matéria dele, para a gente conversar entre a gente, tá bom? Então agora deixa eu apresentar o professor Ettore, trabalha no experimento Dark Side, com respeito trabalhava, né? Com respeito à aula de hoje que vocês vão ter de Dark Matter, e atualmente ele é responsável, é um dos responsáveis Photon Detection System do experimento Dune. Okay? Então, a gente trabalha juntos, né? No experimento Dune, no experimento SBND e no experimento Lariat e também Protodune. Parecem bastante experimentos, mas o que a gente faz é basicamente, a gente se ocupa da parte de fotodetecção. Tá? Por essa razão, ele está deixando essa parte de Dark Matter, pode ser que seja um dos últimos talks que ele vai fazer sobre isso, né? Então aproveite, ele vai falar em inglês, apesar de que o português dele é muito bom.
Não é muito bom.
Mas vocês podem perguntar para ele em português, tá bom?
Perguntas podem ser em português sem problema.
E se vocês não entenderem alguma coisa, por favor, levanta a mão e pede para começar de novo, que ele explica de novo. Tudo bem?
Ou se não entende inglês, vou falar tentar de explicar em português.
Se vocês quiserem, ele pode falar em italiano também, vocês decidem. Tá bom? Então...
Bom dia. This lesson will be on the direct detection of winds. I will review mainly the most important experiment in the field, the most important experimental techniques, so that we have the feeling of how dark matter can be detected, how is effectively detected by experiments. There will be a small introduction about dark matter. Probably there are things that you already know, they are very basic considerations. And then we will start having an overview of the experiments, of the experimental techniques. That is something that probably is less known. So let's start. This is something that everybody knows. The cosmological evidence of the existence of dark matter is very solid. We have a lot of evidences that dark matter exists, that there is a great quantity of non-luminous, but it is not only non-luminous, matter in the universe. The first evidence, the first hint of the existence of this dark matter comes from this guy that was a Swiss physicist, Fritz Zwicky, that tried to measure the mass of the Coma cluster, that is a cluster of galaxies, using two different techniques. The standard one that was based on the luminosity, because estimating the number of stars by the luminosity of the clusters, by the luminosity of the galaxies, he obtained an estimation of the mass of the cluster. He made the same estimation using a dynamical technique, the Williams theorem, where you can estimate the mass of the cluster by the relative movement of the galaxy among each other. It's a completely different technique that is based on the gravity. What he obtained is that a very striking result. The two estimations was completely different. There was an order of magnitude difference between the two. The estimation by means of the gravitational technique, the Williams theorem, gave an amount of mass 10 times higher than the amount of mass estimated by luminosity. He concluded that there should be a great amount, a dominant amount of matter that was not luminous. More or less, few people believed that he was right because he was a quite original physicist. So he passed more or less without any kind of recognition of his work. Many years later, in the 70s, there was a physicist, very popular now, that is Vera Rubin, that performed a very systematic study. He measured the velocity of the rotation of the spiral galaxies. What she did is the following. He chose spiral galaxies, that are galaxies that have a central nucleus and more or less, and the disk that contains all the matter is contained in the nucleus of the galaxy. The disk contains a fraction negligible of stars. So she measured the rotation velocity of the galaxy, because the galaxies are rotating as a function of its radius. So, if we assume that the distribution of matter is dominated by the distribution of luminous matter, if we assume that all the matter is concentrated in the nucleus of the galaxy, as we see from optical observation, we expect a behavior of this type. If this is the radius of the galaxy, we expect that the velocity grows up to the radius and that then decays with some function of r. I remember when the square root of r. What she observed is completely different. It's completely different behavior. You observe something that is like this. Totally different. For all the galaxies she surveyed. How can we justify this behavior? We can take into account this behavior if we assume that the galaxy is immersed in a fluid of dark matter, of non-luminous matter, that is uniformly distributed along the galaxy. So that the amount of matter is not dominated by the nucleus of the galaxy, but is dominated by the halo, it is called the halo of dark matter. This was one of the first serious evidence of the existence of dark matter. Nowadays, we accumulated many other evidence of the existence of non-luminous matter in the universe. But the point, then I will say to you something. We discovered also we know today what is the nature of this matter. It is not non-ordinary matter. It is not only non-luminous. It's a matter that is made of something we don't know. Particles that, if they are particles, that have not been discovered yet. It's not simply not luminous. Up to the 70s, up to the observation of Vera Rubin, the people thought that it was simply non-luminous matter. With this new observation, principally, the observation of the cosmic microwave background, that is, you know that at the origin there was the Big Bang. So and the universe was very hot. When he started expanding, he started also to get colder. And if you measure the spectrum of this radiation, this background radiation, thermic radiation, relic radiation of the Big Bang, you discover that it is a perfect, more or less, black body radiation. It is the more perfect black body one we know. All of you know the theory of the black body, how is the spectrum, how you can approximate a lot of things with the black body. But in laboratory, everywhere you want, you cannot reproduce exactly a real black body. The only almost perfect black body is the radiation of the universe. That has a temperature of about 2.7 degree Kelvin. But that means, in terms of weather, it is in the microwaves. For this we call cosmic microwave background, because this thermal radiation is in the region of microwaves. But if you go to see at the small variation of this temperature all over the sky, observable with experiments that go on satellite, you discover that there are disuniformities. These disuniformities are related to the story of the universe and to the matter that constitutes the universe. You can infer a lot of information from this plot. And what we understand using this plot, combined with other observations, combined with the standard model for the evolution of the universe, we have a very surprising conclusion. That is, the amount of matter that we know, that we can describe by physics laws, that we study, that are described by the standard model of particle physics, is only 4% of all the energy of the universe. is a very small part of the universe, what we know. The dark matter accounts for the 23% of the energy of the universe. So, is 6 times higher than the ordinary matter. While the remaining 73% is something more exotic. It is dark energy. It's called dark energy. All of you know that the universe is accelerating. The expansion of the universe is accelerating. This means if the evolution of the universe were dominated by gravity, we would expect that the universe would expand and get the expansion would get much slower with this evolution because of the gravitational attraction. This is not the case because there is this dark energy that is pumping an acceleration of the universe, and that take into account the great part, the biggest part of the energy of the universe, more than 70%. And we can constrain also the type of matter this dark matter should be made of. It is non-baryonic matter, that means matter made of particles we don't know, not yet discovered. That needs to be called in the era of decoupling of radiation for matter. What does it mean? That when the radiation, up to a certain moment, the radiation and the matter of the universe were very strongly coupled by the electromagnetic interaction. When the universe cooled down, and so the energy of the photons decreased, atoms started forming hydrogen atoms that are neutral. So they don't have electromagnetic charge, and so the photons and the matter decoupled. This dark matter, at this time, that was more or less 300,000 years after the Big Bang, this matter had to be called, that was non-relativistic, to justify a very important thing, the formation of structure of the universe. Because we need this assumption to justify the universe as it is today, with the structure of the galaxies we see today. This is the most striking evidence of existence of dark matter. This is the interaction of two clusters. It is called the bullet cluster. There are two clusters of galaxies that collided. What happened? What you see here is the result of the interaction. Here in the middle, you see the baryonic matter that interacts electromagnetically, and it remained more or less in the middle, in the region of the interaction. You can also measure, and this is measured by optical telescope. You can also measure the distribution of the mass of these clustered galaxies by gravitational technique. We go back to gravitational technique. You see luminosity and gravitation are on the opposite side. With gravitational technique, a technique that is called gravitational lensing, probably you know, because measuring the distortion of the space-time, that due to the mass of the galaxies. Measuring this distortion, you can measure the distribution of the mass of the universe, of the galaxies. And what you see is that the masses are, the mass of the first cluster is here, and the dominant mass of the first cluster is here, and of the second is here. What does it mean? The dark matter that interacts very poorly passed through the dark matter, while the ordinary matter stayed in the middle region of interaction due to electromagnetic interaction. You see dark matter and ordinary matter decoupling, because dark matter interacts very poorly with other dark matter and with the ordinary matter. So they passed through, they separate, while the ordinary matter stayed in the middle because there are hot gases. Is an interaction of cluster of gases, so it's something very energetic. And this is the most striking evidence of existence of dark matter. So so this is something I already. The most plausible, the most reasonable candidate of dark matter is called a WIMP. That is a weakly interactive massive particle. That means a massive particle has a mass of the order of 100 times the mass of a proton that interacts only via weak interaction. So it's extremely, the cross-section of interaction is very low. It's like interaction of neutrinos. You know that you attended lectures of neutrinos. You know that they interact very poorly. That you need a big detector to detect them. The cross-section of the dark matter is lower, is much lower than the cross-section of neutrinos. So, but there is a small chance that they interact because they interact by weak interaction. So, if I build a detector big enough, sensitive enough, some dark matter particles, some WIMP, from time to time will deposit some fraction of this energy. And I can detect it. I can think to detect this energy. Basically, all the detector, particle physics detector, can detect all the ionization produced by this energy release. But for example, this WIMP hit nuclei of the material. The nuclei recoil inside the material and ionizes the surrounding atoms. So, or it can produce scintillation light. There are many detectors that use the principle of scintillation. That is, when there is an energy release, the material emits a flash of light that I can detect. Or, this is a bit more difficult, I can measure the increase of temperature that is produced by the energy release. When there is an interaction, also of particularity, the release of energy causes an increase of temperature of the material. I can take to measure the heat. There are experiments that measure this. Just to have an idea, the difference of temperature before and after the interaction is of the order of the millikelvin. So you need to build a detector that works at a temperature of millikelvin, because you can't have a detector at room temperature and you want to measure a difference of temperature of 1 millikelvin, 10 millikelvin. You need to have a background at least comparable to the signal. And a lot of experiments measure two of these observables. For example, scintillation ionization, heat and ionization, scintillation heat, because this allows to discriminate particles and to discard the background of the detector. Because you need to think that you are searching for extremely rare interactions. Interaction that nobody observed up to now. So you need to have an extremely sensitive detector with an extremely low and controlled background. Okay, sorry, this is in Italian. I didn't have time to translate. So what happens in dark matter experiments? So typically you do not detect nothing. So if you don't detect nothing, you can put a limit. What are the parameters we don't know? The mass of the particle, the cross-section. So if you do not observe nothing, you can say, okay, in the regional sensitivity of my experiment, I can exclude all the parameters that will give a positive signal. I can do an exclusion plot. I exclude the region that will give a positive signal in my detector. you do an exclusion plot. In the case you observe some signal, you can identify a region in this space of parameter, cross-section and mass of the WIMP, where you can say, okay, the parameters of the WIMP, characterizing the WIMP, is in this region. This is what typically is done. If you do not observe nothing, or you observe something that is compatible with the background that you have to estimate, you put a limit in this plot. If you observe something, you describe a region of the allowed parameters that would be compatible with your observation. So this is the actual scenario of dark matter search. There are a lot of experiments, so it's very complicated. The situation is very complicated because we don't know what it is. We don't know what model is the best to use, and there are a lot of experiments making measurement. There are some claims of observation of dark matter. These lines are exclusion plot. Region excluded by some experiments. But as you can see, here there are regions where some experiment measured something. They claimed to have observed dark matter, and so they defined a possible region in the spatial parameter of the mass and cross-section of the WIMP. You see that the situation is confusing because here you have the signal, but all the region appears to be discarded by other experiments. Because even if these regions are discarded, they are discarded on the basis of some model. People measuring the signal, for example, of the DAM experiment, say, no, you are excluding this my signal because you are relying on a particular model of the standard WIMP model. But WIMP could be something different that interacts only with the electrons, does not interact with the nuclei. So you can't exclude my observation. So we are still in this. But the point is that there isn't clear evidence of detection of dark matter without any kind of doubt. All these signals are more or less very controversial. Let's start with the first experiment that started this more or less desire. Is the DAM experiment. This experiment is installed in Italy in the Gran Sasso laboratory. That is an underground laboratory. It is working since 15 years, more or less. It is underground. All these experiments are underground because we have, as I told you, we are searching for rare signals. So you can't expose the detector in surface because you have the cosmic rays. In surface you have 1 million cosmic rays per square meter per second, per hour. So you will continue to observe muons, cosmic rays. Your detector will be completely blind to everything else. So you need to go underground. All these experiments are underground. What the DAM experiment is measuring? It is measuring one of the characteristic signatures of the dark matter signal. That is the annual modulation. Because imagine our galaxy, that is immersed in the WIMP halo. The sun, our sun that is here, is moving inside this WIMP halo with a certain velocity. And the Earth, we are moving around the sun during the year. So there is one period of the year when the velocity of the Earth is parallel to the velocity of the sun. So we are in this situation. So the total velocity, this is the sun, this is the Earth. So the total velocity of the system of the Earth with respect to the halo of WIMP that is assumed to be stationary is the sum of the two velocities. After 6 months, the situation is reversed because the Earth will be on this other side, and the velocity of the Earth will be the velocity of the Sun minus the velocity of the Earth, because they are in the opposite direction. The Sun is going in direction, and the Earth is going in the other direction with respect to the WIMP halo. So the velocity of the detector that is in the laboratory is different during the year with respect to the WIMP halo. This causes a difference of the signal, because you expect to have more interaction when the velocity of the detector is higher with respect to when the velocity is lower. So you expect to have more interaction of dark matter in the summer with respect to winter. So you expect a signal, if you do a plot of time versus number of interaction, you expect something that is like this during the year. And this is exactly what has been observed let me show what is the signal. This is exactly what they observed. They observed for 11 years, that is a solar cycle, the oscillation of the signal, and it has the right parameters of oscillations. It is very well, it is more or less exactly what one would expect for a dark matter interaction modulation signal. How is the, let's go on the side of the detection. How is done, what is the configuration of this detector? It is the first one, is the historical detector of dark matter. It is made of crystals of sodium salicylate, of sodium iodide, that is a scintillator. Probably all of you in your didactic laboratory used the sodium iodide scintillator coupled to a photomultiplier. You probably use the gamma source to excite scintillation and detect it with the photomultiplier. Here the sense is the same thing. There are crystal of sodium iodide that are doped with thallium. Each crystal has a cylindrical shape, is 10 kilograms, and it is observed, and there is an array of this. There is an array of this scintillator. In the first version of this experiment, that was called a DAMA, dark matter, there was an array of 10 crystals for a total mass of 100 kilograms. It is important to have a segmented detector. Then I will explain you why. Each crystal was observed by 2 photomultipliers. You had the crystal observed by 2 photomultipliers on the 2 ends. So, when hypothetically a WIMP interacts, produces a flash of light that is detected by the photomultipliers. All of you knows what is a photomultiplier, so you need that I say something about it. You don't know what is a photomultiplier? Okay.
Was explained yesterday.
I was explaining yesterday?
Yes. Nobody remember.
Okay,
No?
let me briefly say what is a photomultiplier. My old friend said that is a photomultiplier is a lamp, the opposite of a lamp. Because a lamp, you give electricity and produces light. A photomultiplier, you give light and obtain an electrical signal. So how it is very simple. It is like an old valve. It is a vacuum device that is made typically of glass, of special glass. When you have the window, when you expect to detect photons, and then you have the multiplication chain. What happens? This is all in vacuum. A photon reaches the window, crosses the window that is made of glass, so it needs to be a visible photon, more or less. On the opposite side, there is a material that is photosensitive, that is very easy to do photoelectric effect. So the photons, due photoelectric effect, is converted into one electron. Here there is an electrical field that focuses the electron toward another electron. So you give enough energy so that this electron here, hitting this electrode, secondary electrode that is called D node, produce 2 or 3 electrons. So from 1 you go to 2, 3. Then you have a series of other electrons of this type, where at each step you multiply the number of electrons by factor 2 or 3. At the end, you have 10, 12, 14 stage, you end with 10 to the 6 electrons from one photon. A signal that you can measure with an oscilloscope. You see this signal on an oscilloscope very easily, without any amplification or without nothing. What is the parameter that characterizes the photomultiplier? Just to close this fast. It's the quantum efficiency. How many photons? If I send on the photomultiplier 100 photons, how many photons I detect? Typically is 20, 30, 10. It's something around 10-30%. So it's able to detect one photon with efficiency more or less 20%. So it's a very sensitive device. It's very used in particle physics. It's the most used device probably used in particle physics in all times, always. From when it was invented in the 50s up to now. So you detect this light with these photomultipliers, and this is your signal. You have an array of these crystals. Why? Because the most dangerous background for dark matter experiments are neutrons. Because neutrons produce exactly the same signal of a WIMP. Because the typical signal of a WIMP is the elastic scattering on a nuclei, mediated by weak interaction. What does a neutron do? A neutron does more or less the same thing. An elastic scattering, depending on the energy, low energy neutrons. An elastic scattering on nuclei, but mediated by strong force. So the cross-section is much higher. So if your background of neutrons is uncontrolled, you will never see dark matter. You will always see neutron interaction. And you are not able typically to distinguish between neutrons and dark matter interaction. But if you have an array of these crystals, we know that the cross-section for strong interaction is much higher. So a WIMP will interact typically. It is impossible that you have two WIMP interactions in two different crystals. The signal of WIMP interaction is one interaction in one crystal. Dot. Full stop. A neutron will make many interactions. Is very likely to produce many interactions in different crystals. So if you see a neutron-like signal in different crystals, a WIMP-like signal in a different crystal, you are sure that is a neutron, and you can discover. So it is important that the detector is segmented. Let me see. Just to give you an idea. The background of this experiment needs to be very low. What are the most dangerous background in dark matter kind of low rare event search detector? The background at the potassium 40 that you find more or less everywhere. And uranium and thorium that are found in all possible material, metals, everywhere you found uranium and thorium. And you need to keep very low this contamination, because they can mimic, because they can produce alpha particles that in some particular condition can mimic the signal of a WIMP. So, to have an idea, the content of this contamination in this crystal is of the order of part per million in potassium. Part per million, yes. For each million of atoms of the crystal, there is one potassium 40. 0.02 parts per billion in uranium and 0.02 parts per billion in thorium. What is the most critical point? Typically, you can produce crystal very clean way. Very clean way. You can grow. There are professionals, farms that do this by the work. The most critical point is the photomultipliers. The photomultiplier typically is the biggest source of background. For this reason, today there are a lot of effort in trying to find a new solution, to find new photon detector with respect to photomultiplier. And one solution is to use silicon device. Probably if we have time, we will talk about it. So as I told you, the detector was installed in Gran Sasso National Laboratory. I want to show you what is the scheme of the shielding of the detector. Because this detector is 100 kilograms, 250 kilograms in this upgrade. It is very small, but it's a very big shielding. If you go one day in Gran Sasso, you see that there is a lot of shield of this detector. From the outside, from inside, you find a 30 centimeter of polyethylene, paraffin, cadmium, lead, and copper. And you have more, 1 meter of concrete toward the surface of the galley, of the tunnel where it's installed. Why you need such a big screen? You need to be screened. You need to be shielded against first neutrons, second gammas. Gammas rays that can produce interaction inside the detector, and electrons and alpha particles. So the polyethylene and paraffin screens neutrons. Because to screen neutrons, you need materials that are rich in hydrogen. Because they, as I told you, neutrons interact with the nuclei. If you want, for example, I want to screen neutrons with lead, you will not succeed because lead is a heavy nuclei. So the neutron will bunch on the nuclei that will go inside freely. Because it's like when you throw a small ball on a big one. The small ball will simply be will go back with the same energy. Will simply change direction. So we'll make some zigzag and go inside the detector. So you need hydrogen because at the same mass. So when a neutron hits an hydrogen, the energy is split. You divide the energy, and after few interaction, it is stopped. Then neutron is stopped, is captured. It typically produces gamma rays. So you need something to block gamma rays. And so you put some metals, depending of the type of background you're supposed to have. And sometimes, okay, then we will say, more or less the scheme is this one. You have neutron screen for electromagnetic particles, and the detector is continually flushed with dry nitrogen, because another enemy of this detector is radon. The radon that is present everywhere, it is a noble gas, that it can go inside the detector and then produce alpha particles. So you need to, especially in underground environments, so you need to be you be sure that your content of radon is low. So this box where it is installed is flushed continuously with the dry nitrogen, with low content of radon. So as I told, this is the result. So they claim. Let's go back. So this is the region of the DAM experiment. So their observation is consistent with the dark matter that can be found in this region. Other experiment, let's go faster because other experiment are trying to verify the signal of gamma with the same technique using crystals. One of these is the Kim's experiment that is in South Korea, that is using, instead of using crystal of sodium iodide, uses cesium iodide with more or less exactly the same technique. With two photomultiplier, crystal in the middle. Actually, they don't have evidence of modulation of the signal. So this experiment is not confirming the signal of DAM. This is the usual scheme for the shielding of the detector: neutron shield, lead, polyethylene, copper, continually flushed with ultra pure nitrogen to reduce the radon contamination. Usually, you have a second neutron shield because of possible interaction or energetic cosmic muons. We are underground, but there are cosmic muons energetic enough that that have enough energy to go inside the tunnel. And when they reach the detector, they can do nuclear spallation on the lid and produce neutrons. So you typically put another screen for neutrons. So if muon produce neutron, you block with this polyethylene. Okay. And so you are safe. It has also a mineral oil screen. This is the construction of the detector. So you have an external screen of mineral oil, lead, and then you have the copper. Another experiment on the same line is this analysis. This is being performed in the Canfranc laboratory that is in Spain with the same technology, 100 kilogram of sodium iodide. They are selecting the crystals because the most important point is selecting good crystal with low background. The historical problem of this experiment is that the DAMA has an agreement with the producer of this crystal, the most valuable crystal available. They cannot give to any other experiment. So this other experiment had to do a great work of R&D to produce crystal comparable in quality with the one of DAMA. But now things are going on, so they will have results. Another very important experiment is the CDMS. This is an hybrid detector. That means DAMA detects only scintillation. CDMS detects heat and detects ionization. So it is an intersection between a bolometer and a germanium detector. What is a bolometer? A bolometer is a crystal that you cool down at a very low temperature, around of the order of 10 millikelvin, 10-20 millikelvin. And it's very difficult to go at this temperature. There's only one technique with the so-called dilution cryo generator. You cool down at this temperature. So, as I told you at the beginning, any interaction of the particle interaction, WIMP interaction, this crystal is expected to release an energy that causes an increase in temperature of the order of tens of millikelvin. So, they have thermometer, spatial thermometer, that are evaporated on this crystal that measure the increase of temperature given by the particle interaction. They are able to detect difference of temperature of the order of 10 millikelvin. It is an extremely sophisticated detector, but it works very near to the absolute zero of the temperature, around 270 minus 273 degrees. And simultaneously is a germanium detector. What is a germanium detector? All of you know the diodes. I'm sure you in your laboratory work with that diode. It is the same technology. If you polarize a diode inversely in the inverse sense of polarization, where currents do not flow, you can use it as a detector. And what you collect when a particle interact inside this detector, it produces an electron hole pair that you detect. You detect an electrical signal. They are similar to diodes, inverse polarized in the inverse sense, that allow you to detect ionization signal. Why you use these two variables? As I told you, because they allow you to perform particle discrimination. Because the bolometer measures the total energy release. The increase of temperature depends only on the total energy that you release to the detector, while the ionization depends on the type of particle. In the sense that for a beta particle of a gamma produces more charge with respect to a neutron or a wave. So, if I calculate this ratio of the ionization energy with respect to the total energy, this is detected with the germanium technique, and this is detected with the bolometric technique. This variable depends on the particle type. So I can reject the gamma background that is always present. Is always the most difficult thing to do. So this is what I'm saying. At the same level of energy release, the phonon signal, the bolometric signal, because as you know, the thermic signal is an oscillation of the crystal that you can describe as phonons, as pseudoparticles. It's the same in the case of electron recoil or nuclear recoil. The charge signal is very different. So you have much more charge in the case of electron with respect to the case of neutron, because there is a quenching effect when the ionization density is high. So if you do a plot of energy, thermal energy, with respect to ionization, you see that electrons and nuclear recoils separate. So you discard. If you have signal like this, you can discard, because they are background. You are looking only for signal in this region. Or you can do another plot. This is the detector, for example. This is inside the crystal. This is, they are very small detector. They are of the order of hundreds of grams each one, because to cool down a big mass is very difficult. So they started with the very small masses. Now the masses are increasing, but it's a very complicated technique. Going at this temperature is not an easy job. And the CDMS, this first version, consisted of more or less 30 of this detector, 11 made of germanium and 19 made of silicon, for a total mass of 5 kilograms. So the mass was small, extremely small. Again, the shielding scheme is the same. You have, in this case, you have polyethylene, lead, archaeological lead. We don't have time to talk about this. Just briefly, many experiments use archaeological lead. Lead found underwater that was lost by typically Roman ships. because the radioactivity of the lead is induced by cosmic radiation. So if you find something that has been for 2000 years below the sea, it is no more radioactive, because all the radioactivity decayed. So it's very precious. And is used typically, the most near shielding to the detector is typical archaeological lead. So, what was the result of CDMS? The result of CDMS was an exclusion plot, because in this case they are plotting the energy with respect to ionization yield, that is the ratio between ionization and phonons. That has a constant value, because you remember that we had two straight lines. If you do the ratio of this with respect to this, you take two straight lines. You expect that the WIMP interaction are found here. You have some point, you can discard the majority of them by means of other criteria, and so they were left with two interactions that were compatible with their background. So they didn't observe that much. The next step will be super CDMS, that will be an extremely gigantic detector with respect to the CDMS, with a mass that will be at its last stage of 400 kilograms. CREST, just very fast, is another hybrid detector, but in this case is again detect heat and scintillation. It's a combination of a bolometer and a scintillation detector. Exactly more or less the same technique. With the crystal are different. In this case, calcium, tungsten, and oxygen. And the scheme of the detector is exactly the same. You have a dilution refrigerator that you have all the shielding. The detector is installed in Gran Sasso laboratory again. And the same plot as you see before for the CDMS. These are very, very similar detector. The region where you expect the signal is more or less here. Now the threshold is probably lower, but you expect a signal in this region from WIMP. They observed the signal. Here is not reported, but they, in the last release of 2 years ago, I think, they reported a signal but it was probably so that leads of a region in the space of dark matter parameter, of WIMP parameter, this region. But it is probably due to background, to misunderstood background. With the last version of the crystals that are much more clear, they have this limit that excludes partially this region. But it's an experiment that is developing. Let's go to the field that we are more interested in, the double phase detector. That is actually the most powerful technique for dark matter detection. This technique uses typically a liquefied noble liquid, xenon or argon. You have a volume of, let's say, liquid argon. On top of it, you have a volume of gas argon. It is in thermal equilibrium. It is observed by a series of photomultipliers on top of it. You can put photomultiplier also on the bottom if you want. There is an electric field inside the liquid argon volume. It is called the time projection chamber, and you will understand why. So if there is an interaction inside the liquid argon volume, liquid xenon volume, what happens? Liquid argon, liquid xenon are scintillators, are very good scintillators, are one of the most powerful scintillators that you can find. Just a brief parenthesis, you need to go at cryogenic temperature, because liquid argon has a temperature of 87, 89 Kelvin degrees, 10 degrees above the liquid nitrogen, while liquid xenon is a little bit more warmer. It's 50 degrees mais hot. So, if you have an interaction, the liquid argon or liquid xenon produces scintillation light that is detected by the photomultipliers. This is called S1 signal. But you have also an electric field. So part of the ionization charge is drifted toward the surface of the liquid. Here, you have an additional electric field that extracts these electrons that you drifted toward the surface outside the liquid, in the gas phase. In the gas phase, you have a more intense electric field that accelerates electrons to produce a secondary scintillation, a secondary excitation of the gas that is detected again by the photomultipliers. So, resuming, you have a first signal due to the primary interaction. It is S1, scintillation signal. You drift the electrons. To have an idea, the drift velocity of electrons is 1 millimeter per microsecond. At the electric field they used in these experiments, that is of the order of 500 volts per centimeters. So it takes hundreds of microseconds to the electron to reach the surface of the liquid. So it's a time that you can easily measure with any kind of instrument. If you connect an oscilloscope to the photomultiplier, you see this difference of time. And after this time, there is the secondary signal that is produced by the electron extracted in the gas phase, accelerated, that produces the secondary signal. So it's a signal proportional to the electrons you were able to drift and extract. Okay, you have two signals. The difference in time of the signals gives you the location of the event inside the detector. Because you know perfectly the drift velocity. You multiply by time, you know the position of the event, the depth of the event. The ratio of these two signals depends on the particle type. Because typically depend on the amount of ionization charge you are able to extract. So the ratio of S1 to S2 depends on the particle type. And this is again a discrimination, gives you discrimination power to discriminate background. Okay, I summarize here all of the things I'm saying, so if you have the slide, you can go through and read what Nicholas is saying. The first experiment to give result with this kind of technique is the xenon experiment that uses exactly the technique of double phase using liquid xenon. This is the history of the xenon experiment, xenon 10, xenon 100, and now they are building xenon 1 ton. 1 ton of liquid xenon. It is a great effort because 1 liter of liquid xenon costs $1,000. It is a great, also economic effort. And there are photomultipliers, under the photomultiplier on top and of the bottom of the detector. This is the technique that I explained before. You have the signal S1, S2. This is a WIMP-like event, and this is an electron-like event. So you see that the ratio of S1 to S2 is very different. So you can discard electromagnetic background. Also, in the case of xenon, there is a null observation. This is the variable they use, the S1 over S2, with respect to the energy of the event. They do not observe event in the region of interest or number of events comparable with background. So they put an exclusion. They make an exclusion. You see that all these experiments, many experiments already excluded the gamma signal. Let's go to the experiment very fast. To the experiment that invented this technique. It was invented by an experiment that was installed in Italy. It was called the WIMP argon program. That used the same technique but with liquid argon. that is another noble gas. Much cheaper, because it's present in the atmosphere, it costs more or less 50 cents of the dollars per liter. So you can build big detectors with liquid argon. The technique is exactly the same, with one difference, because the scintillation light of liquid argon is in the vacuum ultraviolet. And the photomultiplier are not sensitive to this light. So you need to convert into visible. How you do this? It's very easy. You use a material that is called a wavelength shifter. You cover all the surface of the detector with this material. So when the photons hit the surface of the detector, the surface are reflected, are converted into visible photons, and then they punch inside the detector and are collected by the photomultipliers. So very easy. Very important for liquid argon is that you have much more discrimination power with respect to xenon. Because in the case of argon, you can do discrimination using the S1 signal, the shape of the S1 signal, that is made of two exponentials with very different decay times. Is a typical signal of scintillation of light of liquid argon is something like this. This is time. This is number of photons. Are two exponential decays. With the first decay is a decay time of the order of 6 nanoseconds. The second one of the order of 1.5 microseconds. So you can clearly see these two decays. And the abundance, the relative abundance of these two components depends on the particle type. An electron gives a signal like this, while a neutron gives a signal with a much lower slow component. So, if you calculate the relative abundance of these two components, you can discriminate particles with the very, very high discrimination power at the level of 10 to the 8. What does it mean? That if I add 10 to the 8 electrons and calculate this ratio, one time I will confuse one electron for a neutron. It's a very powerful technique. While the S1 over S2 give a very lower discrimination power at the level of 100. So, in the case of xenon, you have to take much more care of the backgrounds, because we have less power discriminating it. While in liquid argon, you have much more power. But on the other side, the argon has an internal enemy, that is an isotope, that is argon-39, that is present in natural argon, that is a beta emitter, with the quite high rate, 1 becquerel per kilogram. So if you have 100 kilogram detector, you have 100 decays per second. So it is, and the discrimination power could not be enough. But for this reason, this is what I told you before. This is how it is done, the discrimination. Pulse shape discrimination, a ratio is 2 over S1. This is the region of interest. In the case of the calibration with neutrons, here in the case of the WIM parameters. Okay, let's go. This is why dark side exists, because the dark side decided to use not atmospheric argon. Dark side is another experiment, double phase, using liquid argon with the same technique, exactly the same technique, with the photomultiplier on top of bottom. It is the chamber is 50 kilograms of liquid argon. In this case, the argon is underground argon. They extracted argon from underground because the argon-39 isotope is produced by is cosmogenic. It's produced by cosmic rays. Cosmic ray radiation of the air produces argon-39. So the idea was, if we go underground, we take the argon from underground, where the cosmic rays do not arrive. This argon should be depleted. Should contain much less argon-39. So they went in a mine in the United States, extracted argon from underground, measured, and discovered that it was true. That the content of argon-39 was 1,000 times lower than atmospheric argon. So they built an extraction plant in the United States, extracted this. It was a combination of helium, argon, methane. They purified at the level to be used in an experiment, and they shipped it to Italy. Because this experiment is installed in Italy in the Transasso National Laboratory. Was shipped by ship because to avoid the more irradiation by cosmic ray when you go by plane. And they filled the detector with underground argon. This is a more sophisticated detector with respect to the first one I showed you. The shielding is much more sophisticated. You have this is a 10 meter per 10 meter tank of water to detect cosmic muons and to discard them. In the middle there is a sphere that contains a scintillator that is a veto, an active veto for neutrons. So if a neutron from everywhere enters the detector, it will, with 99.9% probability, produce an interaction also in the active veto that is seen by the photon multiplier. So if I have a coincidence between the active veto and the internal detector, I can discard it because it is an element. This is the active veto description. The location of the detector is the clean room, because the detector was installed from a clean room to avoid radon contamination. It is continually purified by radon, from radon. So the first run was with the atmospheric argon, the first run of 2013. We observed, I say we because I'm working with this experiment, 4 events that were discarded because 3 events were coincident with the neutron veto. And 1 event was had the coincidence with the neutron and water tank. So 0 event in the area of the region of interest, and so you can do an exclusion plot. The run with the underground argon that is still going on, the experiment is working, was released a new limit, that is this one, that improved the limit of the previous run. The best limit in this field are the limit of the xenon and the LUX experiment that are both with liquid xenon. LUX in the United States that uses liquid xenon is exactly the same of xenon. Let me conclude. I would like, since we have Gustavo, that works in experiment, very interesting experiment that is called a tank. He will say something about this technique that is different from all the techniques I showed you, because it's based on CCD cameras, CCD detectors, like the CCD you have in the form. So, Gustavo, if you want to say something about tank.
Sure. The detectors that Ettore has been shown, they typically, you can see, maybe I should go there. You can see that all these limits have a characteristic shape, no?
Let's go back to the first.
That's good.
Okay, that's good.
Yeah. So this is the energy of the wind that we are looking for, and this is the cross section. And the typical plot, when you see this shape, it means that you are limited by background or mass. But at the lower end of the shape, you see that the plot goes up. That typically reflects the sensitivity of your detector. Okay? So this type of detector require that the wind will interact with your detector and produce a signal of some few kilo electron volts or more than few kilo electron volts, on the order of 10, 20 kilo electron volts. And if the interaction produces a recoil with less energy, the detector becomes less sensitive to see that signal. Okay? So this is the typical efficiency or inefficiency of the detector going up. Okay? So the other characteristic that the detectors that Ettore have been showing, many of them, CDMS is in the order of grams or few kilograms. But the noble gas or noble liquid experiments or crystal experiments have a lot of mass. No? Now we are talking about tons of mass for the upgrade of LUX, and even dark side will have a xenon also. No? CCDs are very small devices, only have grams of mass. Okay? But the good thing is that the threshold is very low. So you are exchanging big mass for low threshold. What that means is that you can explore this part of the phase map that these detectors cannot see. Okay? So if you go to the previous plot that Ettore showed before with all the experiments, the dynamic experiment will be able to explore this part of the phase spectrum. No? And another interesting thing is that, Ettore said that it's difficult to explore dark matter because there are so many models that you are never sure how the WIMP will interact with the detector. No? But it's expected that the number of interactions will grow exponentially with the recoil energy. Okay? So this is the number of interactions. So you expect to see more WIMPs for low recoil energies. So this is the advantage of damming, that you will have a larger number of dark matter particles interacting with your detector if you can move the threshold. So this is the idea, no? Moving the threshold to the order of 10 electron volt equivalent. Okay? As opposed to 10 kilovolts, 10 kV. Okay? So we go 3 orders of magnitude lower in the threshold.
Thank you, Gustavo. So there are many new ideas in the field of dark matter. Cannot show. There are many others. Well, this is the standard landscape of WIMP detection.
And the other thing that maybe I should add is that Ettore also mentioned that some models say that the dark matter could only interact with electrons. No? And if you have, of course, the interaction with electrons will produce even a smaller ionization signal. So if you keep moving the threshold down to the sub-EV, then you could see electron recoils. And that's something that we have also in the future.
Perguntas, dúvidas, em português.
Eu não lembro bem o que os cintiladores, eles são ativados com telúrio, o que é?
Sì, questo è tipicamente o talio, porque o material que faz na luz de verdade, porque a interação deixa energia no sódio ou no iódio. depois é transferida para o talho, que faz luz, é uma luz detectável. De doping, todos, mais ou menos, todos os ventiladores têm que ser dopados para ter luz detectável, porque as fotomultiplicadoras são sensíveis e não visíveis. Você precisa de luz visível. Perguntas? Dúvidas?
Você vão ter mais chances de perguntar para o Ettore da escola, se tiver algumas outras dúvidas. E depois a gente também conversa sobre essa questão de página, nós fazemos um estudo aqui, o IFGW, e aí a gente usa o Laboratório Nacional de Lucídio para fazer algumas medidas. Então, depois a gente pode conversar sobre isso também. É muito importante, como disse o Wesley, que você consiga pegar aquela luz que não dá comprimento de onda visível, coloque o comprimento de onda visível sendo evitada pelos fotomultiplicadores. Seja fotomultiplicadores como aqueles, ou como fotomultiplicadores de silício, que é uma nova tecnologia que está funcionando com esse tipo de equipamento. Então, assim, o trabalho experimental, como a gente falou ontem, tem vários subitens e acaba agregando gente em todas as áreas. Né? Se tiver alguém que é especialista em química, a gente precisa também.
Stiamo montando un laboratorio aqui na Unicamp di argônio liquido. Agora vai ser pronto nesse final do ano. Está interessado para trabalhar com tecnologia de argônio liquido, principalmente per neutrinos. Já temos a nossa área de estudar, já trabalha com gente. No na dark matter, principalmente neutrinos, com experimentos no Fermilab. Se você está interessado em trabalhar um pouco nos Estados Unidos, trabalhar com argônio líquido, entre em contato com a Anna, comigo.
Vamos agradecer também, né?
Pessoal, antes de vocês saírem, primeiro todo mundo assina a lista? Eu vou pedir só para Fernando, Marcos, Renan, Cássio e o Saulo para virem falar comigo aqui rapidinho. Os outros podem ir subindo para a foto.
Vamos tirar foto?